a function and write it as a polynomial. Either find the series name for it or kind of doing the approximation. So there's the example we did yesterday where we did a second degree Taylor polynomial for arctangent. And then what we had kind of ended with yesterday was looking at what I call the big five. And we were going to kind of finish those up today and then just barely start kind of seeing what we can do with them today. I didn't want notes to be long today. So I'm only going to keep you for about 20 minutes today so you have time to kind of catch up on homework and just some time for this to kind of absorb in your head and to give you some time to start memorizing those 5 series. So when you're looking at those series, again, we looked at 3 of those yesterday. We had the geometric one, the e to the x one, and the natural log one. How we came up with those is we kind of thought about how they would look when we kind of created that table. And then we looked for patterns, and we saw that that is where that series came from. And what we're trying to avoid is normally we would not want to do this table for every single function that we needed to. Obviously, there are going to be some functions where you need to know that table to create the terms, and then you can create the series. But the idea behind these big 5 is that most of the kind of key functions we deal with all look similar or can be created by one of those 5 series. So what I wanted you to start off by doing today is kind of like a warm-up. We left off with cosine. Go ahead and take some time, again, using that table. And again, I'm not really giving you like a limit on the number of terms to do for it. But go ahead and start generating some of the terms for cosine. See if you can recognize the pattern, and then see, looking at that pattern, where maybe a formula could come from. Obviously, you can click on the big 5 and see the formula, but I think it's useful to kind of see where it comes from. So go ahead and take a little moment to, again, fill in that table for cosine. Things you're looking for is kind of like the first 4 terms, first 3 terms, 5 terms, doesn't really matter. See if you can kind of pick up on a pattern, looking at maybe a pattern with the factorials eventually used, maybe terms that cancel out, a pattern you see in the exponents. So you can kind of see and understand where that formula comes from, and then we'll do the same thing for sine. So go ahead and take some time to do that. You'll see me working as well, but then I'll go back, of course, and kind of explain where that formula is coming from. But go ahead and take a moment to generate a Taylor polynomial for cosine. So there's my table for this particular function. So again, I just went to like the 4th degree, but we do notice, so when taking the derivative, we have like cosine. The derivative of cosine is negative sine, its derivative negative cosine, its derivative positive sine, and then the derivative of sine is cosine, and that pattern is just going to kind of repeat over and over and over again because of how trig derivatives work. I'm centering this at 0. So plugging in 0, we know that the cosine of 0 is 1. So like the derivatives evaluated becomes 1, 0, negative 1, 0. And then that's just going to kind of keep repeating over and over and over again. And then using that kind of term formula, which again, you definitely want to have that format memorized of a generic term of these power series. And we can kind of start seeing some of the terms. We can also make some predictions. So if I'm looking at this one, I already see it kind of goes 2 factorial, 4 factorial. I know all the sign of 0 is always going to be 0. I notice that the signs are on all the odd degrees. So like I know the next term, I can kind of pick up on an alternating pattern here. This next term is going to be 1 over 6 factorial, x to the 6. You could keep going, like I could pick up that the next one will be 1 over 8 factorial, x to the 8th. We know that's going to continue forever. So what's important is kind of understanding how we can write a series for this function. Well, cosine, again, all of them start at 0 except for the natural log one. We see it's alternating, so we know that there would be a negative 1 in it. I'll hold off on kind of putting an exponent on it right now. And then when I kind of look at the denominators, I see we have 2 factorial, 4 factorial, 6 factorial, 8 factorial. It's basically all the even numbers. Even for this 1, like it's technically 0. 0 is not really even or odd, but 0 factorial. How can we create all the even numbers? Well, what's always even? 2 times something. So what's in the denominator is 2 times n, and that factorial always matches the exponent. So we have x raised to the 2n. And again, that would be something you want to memorize. How I ended up memorizing this when I first learned it is cosine has the even degrees and the even factorials. So it has a lot of even stuff kind of going on it. When you think about the actual graph of cosine, that is what the graph of cosine looks like. It's symmetrical about the y-axis, so it is an even function. So that was kind of my reminder when I learned it, that cosine is an even function, so it is the formula that has the evens in it. So we had the 2n factorial, and then also the exponent to the 2n. Questions on that power series for cosine? Go ahead.
What's the exponent for the negative 1?
Oh, yeah. I should probably add that. So thank you. So if I'm looking at it, I see that that first term is positive. So if I want that negative 1 to be positive, we're just going to put an n on the top. And then you can kind of see that that does check out. So like plugging in 1, which will be like the second term we see, that will be the first power, so that's what's going to make it negative. So thank you, Alex. Don't forget that exponent would be an n, which of course different. When we did the natural log one, we used n plus 1. So again, different things that we want to kind of keep organized in our head. Go ahead now for me. So that was cosine, so you can probably do sine maybe even without forming the full table. Go ahead and take a moment to figure out what the sine one is going to be. Again, you can always start out by kind of listing out the derivatives. It being a trig function, there are going to be some repetitive derivatives that we see, so you should be able to kind of pick up on the pattern fairly quickly. And we are going to center this one at 0 since it is one of kind of our basic series. The only one we don't center at 0 is the natural log. But go ahead and take some time to figure out the first 3 or 4 terms of sine, and then see if you can write a formula for the series of sine. And again, I know it's something you can look up, but I think it's a lot easier to memorize something when we can kind of see where it comes from. And it does look very similar, I think, as expected to the cosine series. So take a second to figure out the first few terms of sine, and then see if you can write the sigma notation for the power series of sine. So again, when I'm looking at sine, similar derivative to cosine, just depending on where you're starting at. So it goes sine, cosine, negative cosine, and then we know that that's going to just keep repeating. Still centering at 0. So plugging in 0, it kind of has the pattern again, 0, 1, 0, -1, 0, 1, 0, -1, forever. And then kind of using that term formula, we start generating some terms. Now I am going to kind of ignore that first term. It is just a 0, so not really exciting or that useful. So that first term we see is really just going to be an x. The next term is 1 over 3 factorial, and it's subtracted x cubed. You can probably assume cosine had all the evens, sine is going to have all of the odds. So like the next term, and you can figure out from the table as well, would be positive 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th. And that's just going to continue forever. So writing a series for this one, we are still going to start at 0 to infinity. It is also an alternating one, so we have a -1, and I won't forget the exponent on it this time. We want to look at what goes in the denominator, the exponent we see on the x. Well, looking at this one, I'm actually going to do the -1 first. I see it also starts out being positive. So when n is equal to 0, I am going to let n be equal, n just being the exponent. -1 to the 0th power is a positive 1. And I do want to kind of think about that factorial. So I see the factorials are the odd ones. Two ways you can make an odd. It's going to be either an even plus 1 or an even number minus 1. So I want to think about what would work. So if I have 2n, I see when I have this first term, I need a 3. So how am I going to get a 3? 2n plus 1. So that's what we end up seeing in the denominator. And then we see that the factorial always matches the exponent. So we'll have 2n plus 1 in the exponent. Again, how I remember my sine function, sine is always going to kind of be associated with the odds. So cosine goes with the even. Sine is always going to go with the odd factorials, odd exponents. Why is that? If you think about the graph of sine, it is an odd function. Remember, an odd function looks the same with if you rotate it around the origin, so it looks the same upside down. Since sine is an odd function, it kind of has those odd exponents. I see my plus 1 didn't write. So there we go. That is the series that we have for sine. Again, what you want to memorize for all of these is like what it converges to, which is basically the function, in this case, sine of x. Know the first 4 or so terms, which again, you should know if you also know the third thing you should know, which is, of course, the series. Questions on the Taylor series for sine? All right, so we're just going to do 1 or 2 questions to kind of see where this is used. Because again, I don't want us to keep you forever in class. And so how do we use these kind of series? Lots of ways we can use them. Some we are required to look at in BC, some that we aren't required to look at in BC. One of the ways that we're required to use them, we have seen it before. Like we can use them to approximate values by maybe going out to like maybe looking at just the first 3 terms or the first 2 terms to approximate values. Like I could approximate the sine of 2 using that power series, using a certain number of terms. The other way that we're going to look at using them next is how we can easily generate new Taylor series or new Maclaurin series based off of something that we have memorized. And how do we do that? We're going to use those same big 5, which is kind of why it's important that we have them memorized and we're kind of able to use them pretty easily and kind of recall them pretty easily to create power series for functions that are directly related to those 5 that we have. What will that look like? It would look something like this. Write a Maclaurin series for f of x, which is equal to e on the square root of x. So let's talk about this problem. It says a Maclaurin series, so we know that automatically it would be centered at x is equal to 0. And Maclaurin series is technically a Taylor series centered at zeros. And then there is a long way to do the problem. The long way to do the problem is, again, to set your table. You have your degrees, you have your f of n, you have your f of n's evaluate at 0. And then you have to create all of your terms. And then once you create all those terms, you would have to figure out a formula to use. Which is doable. Like, you could do that. It is allowed, it is correct, it would work. When it comes to doing these, though, that's definitely not the most efficient way. Like, you still need to know how to do it. There are going to be some functions that maybe aren't related to the ones that we're looking at, or maybe it asks you to use the table. But there are going to be shorter ways to do a problem as long as you know those 5 key power series. And how we do that, and I'm just going to kind of rewrite it below it, is we have this f of x, which is equal to e on the square root of x. And we want to figure out which power series would this one be most closely related to. Well, I think it's pretty obvious which one is it most closely related to. Looking at the list, e to the x is clearly the one that's going to be most related to e raised to the square root of x. So I'm going to go ahead and write that one down. So this is memorized. E to the x is equal to, it's the series starting at 0 to infinity of 1 over n factorial x to the n. And again, that is something that we will have memorized, whether you have it memorized now or later. And it feels weird, but what we're going to do is we're just going to kind of force different ways to manipulate the problem. Things you sometimes do. Maybe you're going to multiply by something on both sides. Maybe you're going to divide by something on both sides. And then what I think feels the strangest for a lot of students is you can just replace x with whatever you want x to be equal to, maybe a number or maybe another expression. Why can you do that? In these cases, like the n is the thing that's changing, you're plugging in different values for n. So x isn't a constant, but we can kind of think of it like a constant. So we can just kind of manipulate it and rewrite it however we want. What do I mean by that? This is probably the shortest version of one. This is e to the x. I want this to be e to the square root of x. So all I literally have to do is whenever I see an x, I just want to replace it with the square root of x. And that feels weird, but we're just kind of saying like, hey, if that power series is true to e to the x, it also has to be true to e to the square root of x. So again, here's the memorized part. But instead of writing x, we have replaced it with the square root of x. It's a new kind of constant variable, if you will. And that power series would be equal to e on the square root of x. If you did it the long way, that is the pattern you would see. Again, I think it will be a hard pattern to find if you did work it out. I will say on the AP exam, especially a multiple choice question, that will not be an answer choice. The answer choice you always want to get it in is kind of like the nice form. There's not really like a special name for it. It is kind of like the basic power series form, but you want to write it in the form where you have a clear coefficient, x minus c if the c is not 0, and then a clear exponent. So you don't really want to have like the square root of x raised to an exponent. You just want to see x raised to an exponent. How can we do that? So we already have kind of the coefficient. The coefficient is that 1 over n factorial. It's mainly the second piece that we want to try to fix. Well, this is the same thing as saying x to the 1/2 to the nth, which we know is the same thing as just x to the n over 2. So what is a power series that is equivalent to e on the square root of x? It is the power series n is equal to 0 to infinity of 1 over n factorial x to the n over 2. That would be considered to be in kind of that clean, nice form. We have the coefficient, and then we have x raised to a clear exponent. Sometimes there might be some follow-up questions. Maybe it asks you to go ahead and list out maybe the first 4 terms, or maybe it asks you to write a second degree polynomial where you plug in values all the way up until you had an exponent of 2. But if it just asks you to find the power series, this is the power series, and you can just stop there. Questions on that? Because I feel like when students see it the first time, they just feel like they're kind of making up stuff, and you aren't really making it up, but you're kind of just like changing it to make it look the way you want it to look.
Mr. Brown?
Yes.
At the top there, you wrote e to the x is equal to all of that. Do you have to write that every time, or can you just jump straight to?
You can jump straight into it.
Right.
This is mainly what I'm just pulling from my head. But you don't have to show steps for one like this. I wouldn't. Let's try, what time is it? Let's just do one more, and that's where we'll stop at for today. Try that one for me. A little bit more complicated, but again, how you approach these, you want to think about the big 5. Again, normally these will be memorized. Go ahead and peek right now, because I'm sure you haven't had time to memorize those 5 now, which is fine. But look at the big 5, figure out which one that one is most closely related to. It should be pretty obvious. And I would recommend writing down that series and just think about how you can manipulate it. You can multiply by things on both sides, you can divide by things on both sides, and you can just replace the x with something else. You can replace the x with a number, or you can replace the x with an expression. So take a moment to that one. Again, it won't take too long to do, but do make sure your final answer is always in that nice form of like you have a clear kind of coefficient expression, x minus c if there is a center, raised to, I keep putting in there, but raised to some exponent, where that exponent is just n, or like an n, or an actual expression. So take a second to try that one, and then we'll kind of wrap things up for today. So if we're looking at this one, I think it hopefully is pretty clear. Like when we see a natural log in the problem, the series that's going to be closest to it is the one for the natural log of x. Again, that is something that you will eventually have memorized, but it is the one that starts at 1. It's also the only one centered at 1. And it is another one of our alternating series that we have. So I'm looking at this one. I do want you to kind of think about the long way to do this one. If you did the long way and start having to list several derivatives, this is not a fun function to find the derivatives of. Like there's a product rule with the chain rule. And as you kind of keep doing that, it gets like messier and messier of a derivative. So then you have to do all that work. And then once you have those terms, you still have to figure out a pattern, which can be relatively difficult, especially for a more difficult problem. So when it comes to manipulating one of those known series, you can either do it one step at a time. Some students like just doing one step at a time. Some students just like doing it all at once. Things that I look at first off, so I see there is an x squared in front. Well, how can I fix that? I can just multiply by x squared on both sides. Again, why can I do that? We're kind of treating x like a constant here because what's really changing is the variable n. And then the other thing I notice, we do have this 4x plus 1. So instead of x, I'm going to change that x into a 4x plus 1. So I have x squared times the natural log, and we're turning that into a 4x plus 1, is equal to the series where n is equal to 1 to infinity. This first part just has a bunch of n, so we're not really touching it. x is going to become 4x plus 1. We still have that minus 1 to the n times x squared. So there's the 4x plus 1 I plugged in. And then we have the x squared we multiplied on both sides. That is a series that works.
Would you not?
Go ahead.
Yeah. Would you not change the x squared into 4x plus 1? Squared?
So the only x I'm replacing, good question, is just the x inside the natural log. So like this x squared, we're multiplying on the outside. Like it feels weird because I know it's a variable, but it's kind of like you're just multiplying by a constant on both sides. And I just wanted my final answer to have an x squared on the outside, so I wanted it to just stay as an x squared.
If you did change it, would that mess you up, or it wouldn't matter because they're all constants?
I'm trying to think. I would say it would mess you up because this x squared, the x that's being squared is the one that's being multiplied by 4 and then added to 1 on the inside. So like you just think about terms of numbers, like this is the natural log of like 4 times, could be like 3 plus 1. You wouldn't like, you're not really plugged, like, how can I say it?
No, I got you, because
yeah, like it would just mess you up.
Out. Yeah, but like based off what we're doing, which is just substituting in, like it made sense to me to just put it in. Like, why is that wrong though? Like, does that make sense?
Yeah, and I'm trying to think of a good way to explain it. The short answer again, so like we're using a lot of the same variables, but like this x in the original series is not the same thing as this x inside the 4x plus 1. If that makes sense. So we're not trying to just convert like all the x's, like not like x is not equal to 4x plus 1. Like that specific x is what's equal to this new 4x plus 1. So they're not all like, we see an x there and an x here, but they aren't talking about the same number, which I know is confusing when normally when we have variables, we want them to represent the same thing. If that makes sense. I feel like I'm not explaining it well, but. So that's, yeah, and that's how, and I think part of it is like try to make it as simple as possible, because we're still going to have to simplify this to get it into that nice form. And just think you want to do as like few steps as possible and keep it as simple as possible. So like the fewer changes you make, the easier it's going to be to kind of simplify it. So when I'm simplifying it, mainly it's this kind of messy part at the end that I have to simplify. Well, the plus 1 and minus 1 cancel out. So that's going to become 4x to the n times x squared. That 4 is going to be part of a coefficient. So I'm going to like distribute that in exponents, and that's being multiplied. So we have like 4 to the n, x to the n, x squared. 4 to the n, x to the n, and x squared, same base. What do we do when we have the same base? We can add those together, and that becomes x to the n plus 2. So this series, x squared times the natural log of 4x plus 1, is equal to the power series from 1 to infinity. Have your clear coefficient, so -1 to the n plus 1 over n. I'm also going to move that 4n up into the numerator since it is part of a coefficient term now. And then we have x, now centered at 0, raised to the n plus 1. And so this function, and you could check it in Desmos, is basically equivalent to the infinite polynomial generated by that power series. Looking at that power series, again, I think it's easy to imagine if you did this the long way with a table, you're probably not coming up with a formula that looks just like that, especially with that kind of 4 raised to the n in there. But that's basically how we're going to kind of start off looking at these. I still have some more examples to do. I'm going to kind of save them for Friday. But are there any other questions that I can kind of explain on that problem? All right. So to wrap up class, what I kind of want you working on, if I figure out where I put it at, just kind of using like the rest of the class time today to make sure you're kind of caught up and where you need to be with these topics. So at this point, you should be able to finish all of homework 7. And if you haven't finished homework 7, like that is the first priority that I kind of want you to get down. Homework 8, it's actually, I know it's weird, it's on 2 different pages in OneNote. There's like one of the book's pages are on one set, and then the other set is on another page. Mainly, first off, because I did honestly forget to attach it to that page, but also it is a nice division point of like where the material is kind of stopping and starting at. After you do homework 7, the first half of homework 8 is mostly problems where you're just creating the Taylor series using that full table and making sure you're comfortable with that table and using that table. The second half of homework 8 is going to be like those last 2 questions we did today, where you're going to use one of those big 5 to kind of quickly generate a new series. Where we'll kind of pick up tomorrow, again, I'm only going to be a goal, I went a little bit over today, but my goal tomorrow is to just do 20 minutes of notes, just to kind of practice more with these kind of series and kind of making sure we're understanding them. And then we'll pick up on Monday with a lot of the more complex stuff that we can do with the series. So I'm going to go ahead and end class here at this point. I did also, and again, some of you may be like this or not, but I do have video recordings I pre-made from everything I did in the spring from last year. It does stop at the big 5 because that's where the AP exam ended last year. But there's just some more detailed notes of those topics if you're interested in wanting to kind of watch any of those videos. But really what you want to kind of focus on before tomorrow is definitely getting homework 7 done and then kind of looking at least at that first half of homework 8. So if you have any other questions, like feel free to stay behind in the meeting. If you're a good